right, this is Emily with Encyclopedia. Today we're delighted to welcome Professor Dr. Blaž Likozar, who is the editor-in-chief of the journal Processes. And today we'll be talking about his research on continuous production and catalysis optimization in chemical industry processes. Welcome.
Thank you.
So to start us off, I have some questions, but before we get into too much of that, could you share with us a bit about your academic journey and what inspired you to focus on chemical process engineering and catalysis optimization?
Oh, yes, very gladly. So basically, chemistry was one of my favorite subjects from the primary school onwards. And there was a bit of a dilemma at the end of the high school. And it was like a very, all over the place dilemma from, philosophy all the way to chemistry. But then at the end of the day, chemical engineering kind of won. And I enrolled at the university for these specific studies because it also had some kind of, let's say, applicative component to it. And I was basically never really sorry considering my choice or the choice that I've made, because it's a very, let's say, interesting and vibrant field, always changing, and there are always some new challenges. And I think that when you look at it, when you look at chemical reaction engineering and catalysis, it's basically in the heart of chemistry and chemical engineering, so some kind of chemical transformation. And nowadays, today, I mean, we have catalysis in more than 99% of our chemical production, which makes it a key enabler in the life as we know it.
Yeah, a very key process, a very key point of how the science all functions. So as editor-in-chief of Processes, what vision do you have for the journal's role in advancing research in industrial chemical processes and in sustainable production?
Yeah, so chemical engineering, which Processes so diligently covering, is basically faced with ongoing challenges. So let's say the birth of the chemical engineering as we know it was primarily distributed between England, and then it had its boom with the advent of oil and gas industry in the US. And of course, we know now a little more than 100 years later that we are facing several challenges. So one of them obviously is on the side of the feedstock. So this means that we are more and more looking at more sustainable carbon sources like CO2, like biomass, maybe potentially also CO2 from the atmosphere. But then again, we also face the energy side of things. So a lot of chemical reactors, as we know them, are powered by natural gas-based energy supply. And nowadays, a lot of effort is oriented towards electrification or let's say, solarization of processes. And a kind of third key challenge is, of course, the digitalization. And digitalization is basically so as to do the optimization of the processes as we know, but at the same time, the new, let's say, the new generation of processes should be much more flexible and fast responding, which is corresponding to the energy source. So if we deem, for example, PVs and then electrolysis or some other type of electrification, we have a much more swift changing of the operation as we were used to. So this is basically something that we also try to push through the priorities of the journal, and we have some, let's say, key fields that are related to, as you've mentioned, continuous manufacturing, intensification, digitalization, and sustainability.
Yeah, and those key elements really help make sure the journalist is staying aware of those processes and how they're ever changing.
Yes.
Will continue to change, especially. So within your work outside of the journal, you've emphasized the continuous production methods in chemical manufacturing, chemical engineering. What are some key advantages of continuous processes over batch production, specifically in terms of things like efficiency and scalability?
Yeah. So nowadays, it's not only being continuous, but also being flexible. So as you mentioned, there are several upsides or advantages to the continuous processing or manufacturing. And this is basically a high level of integration and hence also better optimization possibilities and intensification in general. But at the same time, we see that there's a constant need, or more and more, there's a need for flexibility as well, either on the feed side. So we have the change in feed. So, for example, if you look at replacing natural gas with hydrogen, typically, if you want to make the process economical, you kind of have to replace a lot of hydrogen at the peak hours of the day, and then perhaps if you don't have a large enough storage, then turn it down a bit later on. So this is the flexibility that I'm mentioning. So that's why, especially within Europe, there was a term coined that's called twin transition, which means that it's a simultaneous digitalization and sustainability transition, so the green transition, so-called. And this is everything that kind of affects continuous processes as we know them. So efficiency, optimization, better yields, and also nowadays more and more flexibility.
Yeah, being more applicable to a lot of modern changes, it sounds like. Yeah.
Yes.
So in your recent research, you developed a CFD-based methodology for monolith catalyst design. Could you explain how computational modeling accelerates catalyst optimization and reduces the cost of these kind of applications?
Yes, gladly so. So this is just an example of how digitalization is basically changing industry in general. So what we've been doing over the last 10 years or so is that we've been trying to apply these so-called multi-scale models, either to the discovery of materials. So in this case, it's more, let's say, lower rank, lower scale models, atomistic to mesoscale. But then again, we have to link those with realistic operations. So we are kind of going from really ab initio DFT-based models all the way to the mesoscale into flow at the end of the day. As you mentioned, computational fluid dynamics are the, let's say, flow equivalent of such a tool that helps to devise, let's say, unit operation type equipment like reactors or other type of upstream and downstream equipment. But one thing we wanted to do more as on top of that is to try to seamlessly, at least to some extent, link the discovery of materials with the optimization of the equipment. And that's why we've tried to integrate the atomistic level and mesoscale level models with the flow, the CFD. And what we see lately is that there's also a lot of, let's say, hybridization with data science, so a lot of machine learning or AI-based models, which basically do not completely replace the mechanistic models, but they streamline and make them much faster.
Yeah, and that integration and streamlining definitely would decrease costs and make things smoother, yeah. As you kind of touched on a bit, catalysis plays a really important role in green chemistry and that sustainability manufacturing shift that is happening. So with regards to that, what are some emerging catalytic technologies or materials that you think show a lot of promise in reducing that impact, especially in regards to chemical production?
Yeah. So if we look at the traditional chemical production and processing, most of the unit operations are thermocatalytic, meaning that with the heat supply to deliver energy, basically the catalyst is able to perform its function. So these are typically high temperature processes that are extremely active, but obviously in some instances the selectivity is a bit lower because you have some difficulties and challenges in controlling the temperature in such a bulky equipment. So what we see nowadays, and this is let's say a trend for quite a few decades now, is that there is this justified push towards sustainability in powering and at the resource side. And this basically also touches upon the let's say, types of catalysis. So one that is, let's say, most notorious and most useful in electrification nowadays is electrocatalysis. So basically, the latter is used, for example, for water splitting. So electrolysis has been with us also from basically Second World War onwards on a more industrialized manner. But there's a lot of challenges to it. So you either have, let's say, electrolysis without non-noble metals, but at the same time, you cannot really make it quite flexible. You have proton exchange electrolysis, which is flexible, but entails noble metals used like iridium and platinum. So this is one trend, to make this direct electrification, so electrocatalysis, cheaper, more scalable and more predictable, and especially more stable as well. The next generation coming after that probably is solarification, so basically photocatalysis. The problem of photocatalysis is that it's two-dimensional in nature, like electrocatalysis, but it also suffers from a very low efficiency. So that's presently hindering its broader uptake. So it's still better to have a single unit for solar light harvesting, like PV panels, and then electrolysis is the second step. But both of these have their, let's say, shortcomings. So there's also a lot of activities going towards the electrification of the thermal catalysis as we know it, because the latter can provide for extremely high turnovers that we as the consumers and the industry which serves us is able to provide. And there are two major approaches to do that. First one is resistance or Joule heating, which is quite easy to apply, but at the same time is very inefficient and costly by that matter. And the other type of approach is induction-based heating, which provides for extremely fast responsiveness and very targeted heating, but at the same time uses induction as opposed to conduction or Joule heating. So these are some of the most common trends in catalysis. For all of these cases, you basically have to tune the materials that you have, either having them conductive for electrocatalysis, having them being able to absorb solar light for photocatalysis, and having some kind of conductivity or inducibility for the electrification of thermal catalysis.
Yeah, that makes a lot of sense, and it's interesting that a lot of them have their pros and cons, and you kind of have to weigh how that will tie into what need you're trying to do to suit with sustainability.
Yeah.
Thank you. Very insightful. So you've touched on this a bit. Excuse me. You've touched on this a bit in regards to the digitalization of the industry and many industries, but in regards to that digitalization and Industry 4.0 and how they're transforming chemical engineering, how do you think specifically that AI that you mentioned and machine learning and real-time monitoring, how does that integration into continuous production systems work? How does that enhance the control and the yield of that optimization?
Yeah, I mean, it's becoming quite indispensable in the operation. Let's say having similar kind of approaches was quite common in the oil and gas industry for quite some time now, because a fraction of a percent was really made all the difference in price at the end of the day, and also the refineries had to adapt to the current market prices for different products of the refinery, but it wasn't so common in other type of industries. So nowadays, with not only larger computational power, but also large language models that we know, this has really become a quite powerful tool for optimization. And it's being prudently used basically by quite a lot of industries. not just for the direct optimization of processing, but also, for example, to manage the storage of the materials, to translate operational reports to the technicians doing it. And this, I mean, it's really the uptake in the last few years has really been amazing. And of course, being brought with that are some concerns, considering especially safety and the robustness of operation. But insofar, I think, at least to the best of my knowledge, we've been quite lucky. So there were no major incidents at play that could be blamed on the optimization or digitalization.
Yeah. And you mentioned earlier that AI and technology use really streamlining things does still need that double check from the
Yes.
people who do the specific task as well. So based on some of the things you've said, you've kind of touched on quite a few points, but what do you think are some of the biggest challenges when it comes to transitioning the traditional batch-based chemical plants into that continuous production system? Do you think there are specific industries that are going to be easier to shift or that shift is more urgent and impactful for?
Well, I mean, maybe starting from the other side, there will always be some industries in which this transition simply does not make any sense. So they will stick to boutique or small batch production because it fits flexibility, and this absolutely makes sense where the added value of your product is very high. For example, some of the pharmaceuticals. But it's interesting also that in these traditionally batch industries, like the aforementioned pharmaceuticals, there's been a big incentive to try to go continuous for various reasons, not only for the sake of productivity, but also for the, let's say, seamless kind of operation. And of course, the whole digitalization and optimization of continuous processes is always easier in the industries that have traditionally applied such kind of approaches like oil and gas and base chemical. But when you come to the other end of the spectrum, the industry is, boldly venturing into doing so. But as mentioned, there's always, if you take it with a grain of salt, there will always be some sectors or maybe specific niches of operation where this will simply not make sense.
Yeah, it only works and helps improve efficiency in things if it genuinely is applicable in a way that's efficient.
Yes.
That makes sense. Thank you for that. So with all of that in mind, looking to the future and how things are shifting, what are some policy changes or innovations in regards to policy that you think are really critical in achieving those sustainable goals, that cost-effective change in chemical manufacturing on that global scale?
Yeah, so there's quite some challenges in this regard, especially when it comes to renewables in general. So it's a big, let's say, venture and business opportunity for sure. But if you look at it strictly from the thermodynamic or the physical perspective, we are basically coming from an era where we were mostly exploiting and using resources that are extremely energy rich. So the molecules of oil and gas have a large, let's say, energy potential, a lot of energy stored in them chemically. And now, because of sustainability, we are more and more turning towards exploiting molecules like carbon dioxide or water for hydrogen production, which are extremely inert and really difficult to split or usefully convert further. So this basically means that we either need to produce much, much more energy that we used to because we have to invest it in converting and splitting these molecules, or it means that we have to get used to consuming more or paying more for the same kind of output that we had before. And this basically touches upon policy, because this means that it's more of a social question than a technological question. So there are, of course, technological challenges, but it's difficult to beat really the basic fundamental physics or thermodynamics. So in these cases, you have to have some kind of social contract or social consensus or on how to approach this. And the difficult part, as you've mentioned, is that there is no global consensus on how to do that, and you will have different approaches to it, all over the globe. And the issue is that, and this is what's in everybody's mind, if you do this transition too fast, you might be, the first on the market, but at the same time, the energy poverty will basically force a lot of companies into bankruptcy. And this is a kind of European scenario that we have right now. So the prices of energy are quite high. On the other end of the spectrum, you have, for example, the US, which is at present very much turning towards fossil resources back, which are, by comparison and sheer physics, much easier to exploit. And then you have, for example, China, which is doing something in between. So there's no single, kind of global consensus on how to do things. And this then comes to the global as well as local policies and whatever different countries or associations of countries like the EU have as a kind of grand strategy. So, but regardless of that, when doing the green transition and going from energy-rich resources to very difficult to convert molecules like water and CO2, this will entail some kind of social transformation as well. So people need to know that having the same level of resources is going to cost them more.
Yeah. And that disagreement on that global scale is a pretty tough hurdle when it comes to this advancement happening.
Yes.
Thank you for all your insights today, for taking the time to share with us all of the information that you know and have, and your opinions and thoughts on how the industry is changing. We really appreciate it.
Thank you so much for the opportunity.
All right. Well, have a wonderful rest of your day.
Likewise.
Sharing time with us.
Thank you.
Take care.